Hello, this is Jack Jackson, and this lecture is going to be on measurements and approximations. So some of the topics we're going to talk about is how to think of measurements as different than pure numbers and compare and contrast these two ways of thinking about numbers. We'll talk about rounding off, some rules for that. We'll talk about significant digits and precision. We'll also talk about scientific notation, some basic units of measurement, and converting between units. So to start this conversation off, let's take a look at a scenario here. Suppose that I'm standing in my driveway and I tell you it is 9 miles to my office. Then suppose I move an additional 6 inches away from my office. Do I now say I am 9 miles and 6 inches from my office? Why or why not? Press pause and think about that just a second. Okay, now that you're back, you're probably thinking this is a little bit ridiculous, right? To say that I'm 9 miles from my office and I move 6 inches away. I mean, certainly, if I was exactly 9 miles away and I move 6 inches further, then I surely am 9 miles and 6 inches from my office on one hand. But it's a little ridiculous because the 9 miles was rounded off to the nearest mile and the 6 inches was not. So we're going to come back to this idea here in a bit. So before we come back to that, let's talk about measurements versus pure numbers. So one way we can think of dividing numbers up is into these two groups. And pure numbers are an abstract concept. And as a pure number, it makes sense to talk about numbers being very precise and exact. In fact, we can even talk about infinitely many digits. So we can take a number like pi, for example, which is an irrational number, and talk about pi having infinitely many digits. We could work it out far enough, maybe somebody could with a computer, and tell us what a specific digit is, but we could never list all of the digits. Okay? And in fact, the only way to actually write pi really is to write the symbol pi. And so, or something that's equivalent to that, but we can never write it out by actually writing out all the digits. At any point that we stop writing the digits, then we have an approximation. So we could certainly say pi is approximately 3, or pi is approximately 3.1, or pi is approximately 3.14159265359. But all of these things are just approximations. Pi is not equal to that. Pure numbers may or may not have associated units with them. Measurements, though, are inherently approximations. These are applied numbers, and they're always rounded off. Let's think about this a minute. So if we're going to measure, say, the length of something, we might take our ruler out and measure it to the nearest centimeter. Or we might measure it more finely to the nearest millimeter. Or if we had some finer measuring device, we might even measure it further down, more precise than that. But no matter where we measure to, we have rounded off to the nearest unit, whatever unit we're measuring to, say to the nearest centimeter, for example. If we can always, at least in theory, measure that closer and closer and closer. So they're automatically, measurements in a real-world setting are automatically rounded off. The only exception to this would be if we're just counting something that's a whole number of things. Okay? But other than that, measurements are always rounded off. These are used in everyday practical applications, and they almost always have some kind of associated units with them. So, for example, as a pure number, we could talk about a square having side lengths of exactly 1. Then the only way we can really say the length of that diagonal, the red the line segment there, the only way we can say its length is exactly the square root of 2. It's an irrational number. Now we can approximate square root of 2 to a certain number of decimal places, but as soon as we do that, as soon as we stop writing those decimals down, then we have approximated this length, and it is no longer exactly the correct length. It's only an approximation of that length. Whereas the exact length is exactly square root of 2 if the sides are exactly 1. And this is an example of pure numbers. We know the infinitely many digits. We know this is 1.00000000 infinitely many zeros. And we know this square root of 2. We know there's ways to work out all of its digits. Contrast that with the figure on the right. It's basically the same figure, but this time it's a measurement. So this is actual physical square that we may build, and we've measured its sides to the nearest hundredth of a centimeter, and they both measure out to be 1.00 centimeters. So using 1 centimeter for the sides, we again get square root of 2 for the diagonal. But this time we do not know that it's exactly square root of 2 and know all those infinitely many decimal places because we only measured the sides to the nearest hundredth of a centimeter. 3 significant digits. And so we have 3 significant digits of the nearest hundredth of a centimeter for our diagonal. It is 1.41 centimeters. Of course, square root of 2 is about 1.41 for some other stuff. So it rounds off to about 1.41 centimeters. So that is a measurement. It makes no sense to talk about that diagonal being square root of 2 at infinitely many decimal places. Or neither does it make sense to say that it's 1.4142135662 centimeters, which is square root of 2 to as many decimal places as a TI-84 will tell you. Well, we don't know all those decimal places. We don't know that diagonal measured that finely because we didn't measure the sides that finely, that precisely. So in the real world situations, almost always we're dealing with measurements which are inherently approximations. So we've mentioned rounding off. Let's talk a little bit more about what that means. So the first thing we want to do when we're rounding off something is choose a precision. In other words, we want to specify which place value that we want to round it off. Are we measuring to the nearest centimeter, the nearest tenth of a centimeter, the nearest hundredth of a centimeter, the nearest meter, the nearest mile? Very different amounts that we could measure to. So we want the decimal number that terminates at the specific place value that we've set aside, but it's the closest to that measurement. So, for example, let's look here at this number line. So here's a portion of a number line here. And if we want to say, well, what numbers round off to 7? Well, we want to know all the numbers which are closer to 7 than they are to any other whole number or any other integer. Okay? So they're close. The numbers that you see shaded in red there on the number line are closer to 7, say, than they are to, say, 6 or 8 or any other number, any other whole number or any other integer even. And so we would get that. Now, we do have a couple of places where they're tied. If it's exactly 6.5, then it's really equally close to 6 and to 7. So we have to decide what to do with that one, about whether we round it up to 7 or down to 6. Now, I have seen some books use some complicated schemes, but I'm going to use a very simple one, and there's a reason for it. If the 6.5, we're going to round up. Because what if you have a number that's 6.50002? Well, that's actually closer to 7 than it is to 6 because it's on the right side of 6.5. So that should round up. So 6.5 anything should round up to 7, whereas 6.4 anything, basically, should round down to 6. Okay? So the simple rule is, if you've got 6.5, really no matter, you don't have to look at what's after it. You can just look at the tenths digit. If it's a 5, we're going to go ahead and round up. And for the same reason, then the 7.5 is going to round up to 8. So the numbers you see shaded in green are going to round off to 8. So the numbers between 7.5 and 8.5 are going to round to 8, round off to 8. And the numbers between 6.5 and 7.5 are going to round to 7. So notice that what that gives us is an interval that's closed on the left and open on the right. So bracket 6.5 comma 7.5 parentheses are the numbers, all the numbers that round off to 7. So an easy rules for determining this now are this. Figure out which digit you want to round off to, the last digit that's going to show up in your final answer. Highlight that digit. Then locate the digit to the right of that number. That's the number we're going to consider. If the considered digit is 4 or smaller, just drop it off and all the numbers to the right, leave the highlighted digit alone, we're good to go. If the number that we've considering, the one that's to the right of the highlighted digit, is a 5 or larger, again drop it and all the digits to the right, but this time add 1 to the highlighted digit and regroup if necessary. Okay, so let's see if you can apply these rules. Probably you've seen this before. Round the following off to the indicated places. I forgot what I wanted. I think the first one is rounded to tenths, and then hundredths, and then 4 decimal places. So go ahead and do those now. Press pause and then come back when you're ready to check these. Press pause now. Okay, yeah, the first one was tenths. So notice I want to take 3.4005 and round to tenths. I need to highlight the tenths place. Now remember, to the right of the decimal it's tenths, hundredths, thousandths, 10,000ths, and so forth. So the tenths place is the 4. So I highlight that. I turned it red here. And then we want to look to the digit to the right of that, which is a 0. Since it's 4 or less, we just drop it and leave it 3.4. The next one is round to hundredths. That red 5 is in the hundredths place. So you go to the right of that, which is a 6. We drop the 6, but we add 1 to the 5, so it makes it 123.46. Hundreds place is the 4 in the next example. To the right of that is a 5, so we round that up, so we drop everything from the 5 onto the right and raise the 4 up 1 to a 5. We still need the 2 zeros there, however, for placeholders, so that's 500. Next one is 4 decimal places, so you count to the right of the decimal 4, 2, 3, 5, 9, so that's 1, 2, 3, 4. Fourth one is that 9 that I have in red. The one to the right is a 9, so that's 5 or bigger, so we add 1 to the 9, drop the last 9. Well, when you add 1 to 9, it makes 10, so that's going to put a 0 there, regroup, add 1 over to the next place value of 5 becomes a 6. Okay, now suppose I say it's 9 miles from school to my house, like in the example that we started the lecture with. What does this really mean? Is this an exact number or an approximation? Well, it's an approximation. It's a measurement. So measurements are always approximations. And by what we mean by this is that it's rounded off to the nearest mile. Okay, so let's let D be the actual exact distance. When I say that the exact distance is 9 miles, I really should say approximately 9 miles. What am I really saying? I'm saying it's a number that rounds off to 9, which means it's between 8.5 miles and 9.5 miles. Actually, we include the 8.5, but not the 9.5. So it's between 8.5 miles and 9.5 miles. You can see that on the number line here, kind of represented here as well. This is one significant digit. Now suppose I say it's 9.1 miles from school to my house. Now I've measured it more closely. Now perhaps I've looked at my car and I've measured not only the miles but also the tenths on the odometer. Okay, now this is a little bit more precise. So this says it's a number that rounds off to 9.1. So what kind of numbers would round off to 9.1? Well, it's numbers. Look at what's shaded in orange here. Those numbers round off to 9.1, and that is 9.05 to 9.15. So what you end up doing is you end up subtracting and adding a 5 in the next digit over. So if we're rounding off to tenths place, half of a tenth is what we're adding and subtracting, which is a 5 in the hundredths place. So 5 hundredths is half of a tenth. And that's what we're going to add or subtract. So in other words, 0.05 we add and subtract to 9.1, and that gives us 9.05 and 9.15, and that's what it's between. Notice that that is a smaller interval. In fact, it's 1/10 as long, as wide an interval as the red interval up here when I just said 9 miles. When I said 9.1, I've indicated that I've measured it much more closely. Now, let's look at these numbers, 9, 9.0, and 9.00. Maybe, again, they could be miles, could be any measurement. Now, as pure numbers, those are the same number, 9, 9.0, 9.00. They're exactly the same thing if I'm thinking of them as pure numbers. But as measurements, these represent three different things. They're really the same length, but it has a difference in how precisely we've measured. Okay, so when I say the number 9 is a measurement, what I'm really saying is it's a number, it's approximately 9, even though I might say equal 9. When it's a measurement, it's inherently approximately equal. Okay, so the distance is approximately 9. I'm saying that distance is between 8.5 and 9.5. And you can see that graphed in red on this number line. So the next number line with the same scale, I've used the measurement 9.0. Well, that's between 8.95 and 9.05. Notice that width of that interval is much smaller. In fact, it's 1/10 as big as the red interval above. So saying 9.0 is saying that I'm measuring it more closely. So that 9.0, since it's the same number as 9, those are equivalent measurements, equal measurements as pure numbers, but as measurements, that 9.0, that 0 is there not as a placeholder, but the only reason to put it there would be to show that we had really measured this to the nearest tenth. So that means we've narrowed it down. Suppose we narrow it down even further to a 3 significant digit answer, 9.00, and this interval's kind of hard to even see, it's so small, it's in pink here, and it's 1/10 as big as the green interval, 1/100th of the size of the red interval, which is much, much tighter. It goes from 8.995 to 9.005. Now think about this a minute. How far could the true measurement be off? Well, the worst case scenario is if it's all the way at the left end or almost all the way to the right end of the interval. So let's say we take the left end at 8.5, and we've said the measurement is 9, we could be off by as much as 0.5, whatever our units are. So let's say this is miles. Our measurement could be off by as much as half a mile when I just rounded off to the whole number miles. But if I say 9.0 miles, then the most the error could be is again the left endpoint, but this time the left endpoint's much closer to our stated measurement of 9. It's only off by 0.05 miles. And if I say 9.00 miles, I've measured it even closer, even more closely, and it's off at most by 0.005 miles. Now, I can't just say that it's 9.00 miles unless I truly measure it to the nearest hundredth of a mile. Okay? I can't say even it's 9.0 miles unless I measure to the nearest tenth. So I can't say anything more than what I actually know. So let's give some rules for determining whether a measurement that's given to you or an answer that you give in a final answer, how many significant digits are in there. Okay, and we will assume some following rules that determine the number of significant digits. All non-zero digits in these numbers are considered significant. So there's no question about the non-zero numbers. Its only question is about the zeros. So any digit between two significant digits is considered significant. So for example, 203 has 3 significant digits. The 2 and 3 are automatically significant because they're not zero. The 0 is significant because it's between two significant digits. So that's a 3 significant digit number measurement. The first significant digit is the first non-zero digit on the left. So what this does is tell you some zeros that are not significant. So zeros on the left are not significant since they're only placeholders. So for example, 0.0025, the first significant digit is the 2. And of course the 5 is also significant, but that means those zeros are insignificant. They are there only for placeholders. Or in the case of the first 0, it's only there to help draw attention to where the decimal point is. And the other two zeros are there as placeholders. So this has 2 significant digits. Any trailing zeros to the right of the decimal are considered significant. So in other words, any zeros that are on the far right of your number, but they're also to the right of the decimal point, those are considered significant. So they're not needed as the placeholders. If you were just to erase those zeros, it would be the same number as a pure number. Okay? So they must be there to indicate significance. So first of all, look at this example, 0.02300. The first significant digit is the 2. So the first two zeros, 0.0, those are insignificant. The 2 and the 3 are, of course, significant. And those last two zeros are also significant by this rule. So it has 4 significant digits. Now finally, probably the most questionable one is when you have something like 2,500. Well, has that been rounded off to the nearest 1 unit, or the nearest 10, or the nearest 100? It's kind of hard to tell just by looking at it. So we will assume the least precise interpretation, and so we will assume that this only has 2 significant digits. So any trailing zeros that are on the left of the decimal, but they're trailing out to the right, they are not considered significant unless they're marked. Now, if you want this to be rounded off to the nearest 10, you either need to say it somehow, like 2,500 to the nearest 10, whatever units are, or one other notation we have is to put a bar over the last significant digit. So we can say 250 with a bar over it, then the 0. We've marked that 0 as being significant. If we put the bar over the last 0, 2500, and then the bars over the last 0, we mark it as significant, and in the earlier rule, rule 2 would say the other one's significant as well. So that would be 4 significant digits. Okay? So we assume the least amount if it doesn't say otherwise. Now, this bar over a number has a completely different meaning when it's on the right side of the decimal. It indicates a repeating decimal. So, see if you can do these exercises. How many significant digits are indicated in these measurements? Go ahead and work these out and come back when you're done. Press pause now. Okay. The 3 that are on the first one here, 3.0025, the 3 non-zero digits, 3, 2, and 5 are significant. The 2 zeros are between significant digits, so they're significant as well. So all 5 digits are significant. And the next one, the first significant digit is the 2. So the first 3 zeros are insignificant. So the 2, 5, and 6 are significant. The zeros between, so it's also significant. That's a total of 4. The next one, the 1, 2, and 5 are significant. These other zeros are assumed to be insignificant unless they're marked. Otherwise, they're not marked, so we're going to assume only 3 significant digits here. The last one, the first 0 is there just to draw attention to the decimal point. It's not really needed. In fact, you could even write it without that one. Then you've got 1.020. All of those are significant by our rules. So 4 significant digits. Now notice that when we have measurement, there's an inherent amount of possible error due to the required rounding off. We talked about this a minute ago, where we said, well, the worst case scenario is you're all the way to one end. So let's take a look at this for a second. Let's suppose we have the measurement A is 3.4 centimeters and B is 2.31 centimeters. So what does this mean? This means A is really between 3.35 centimeters and 3.45 centimeters. So the amount A is away from the actual exact value of A. We said A is 3.4, but how far is 3.4 from where A actually is? Well, the worst it could be is if its A is truly 3.35, which is 0.05, this should say. There's an extra 0 here. I'll fix that for the printout. 0.05, that should say. Okay? So we call that amount the maximum round-off error, or the maximum error due to measurement. It's not a mistake. It's just something that inherently happens whenever you round off numbers. So again, this should be 0.05. Yeah, and then this one's also off by one 0 here. So this is 0.005 for B. B could be off by 0.005, and that's as if it's all the way at the left end. I'll correct those two before you get your printout. Okay, so let's look at what happens when we have an addition and see what happens with how far off our projected answer is from what could actually happen. So again, using the same two values for A and B, we get A is approximately 3.4 centimeters, so it's really between 3.35 centimeters and 3.45 centimeters. And we say B is approximately 2.31 centimeters, so it's actually between 2.305 centimeters and 2.315 centimeters. Well, what do we give for A plus B? Well, we're just going to add 3.4 and 2.31. You can do that, should be able to do that in your head or with the calculator as well. And of course, we get 5.71 centimeters. Now, if we just write 5.71 centimeters as our final answer, then we're leaving the impression that we know this all the way down to the nearest hundredth of a centimeter. And so that would be 3 significant digits. At least we would be claiming we have 3 significant digits, and to the nearest hundredth of a centimeter. So that says that we're saying that the sum is in the interval from 5.705 centimeters to 5.715 centimeters. However, in actuality, where could the sum be? Well, the lowest it could be would be if you add in the two lowest ends of these possibilities for A and B. That is, add the 3.35 and the 2.305. And that turns out to be 5.655 on the low end. On the high end, it could go up to, and not include, but it would be bounded by the upper bounds of these two added together. So you could add the 3.45 and the 2.315, and that's going to give you the upper bound of what the sum could actually be. Sort of worst case scenario, which is 5.765. So if we know that the A is actually between 3.35 centimeters and 3.45 centimeters, and B is between 2.305 centimeters and 2.315 centimeters, then we know that A plus B must be between 5.655 centimeters and 5.765 centimeters. But compare that to what we have up above, and that's actually quite a bit wider interval, okay, than what we would indicate if we just had 5.71 centimeters. So when we say 5.71 centimeters, we're actually claiming that we know this much more precisely than we really do. We cannot claim that we know that much more precision in our final answer than we actually know. So it makes more sense to round off to a different place, to round our answer off to say 5.7 centimeters. Now if I say 5.7 centimeters, that says that we're saying that the true answer must be between 5.65 centimeters and 5.75 centimeters. This is not perfect because this is not exactly the same as the same interval that we had before, but it's much closer to what the reality is. Remember, the reality is it's between 5.655 has to be and 5.765, which is much closer to this, this interval here. So this is a sort of, the true way to do it would be to decide to actually give this interval that I have up here, 5.655 centimeters to 5.765 centimeters. That would be the most precise way to give the answer to that sum. But what we're going to do in this class is use a simplified rule where we go ahead and add it together, get the 5.71 centimeters, and then we determine that, well, in this case, the least precise of the two measurements goes to the tenth of a centimeter, and so when you're adding, you go with the least precise measurement, which is to the tenth of a centimeter, so we round our answer to the tenth of a centimeter. Notice that the interval that produces or implies is really still not exactly right, but it's much closer than if we tried to say 5.71 centimeters. We'll do another multiplication example. Actually, we're going to take the same two numbers, okay, and if we multiply these, if we take 3.4, times 2.31, we get 7.854, and of course centimeters times centimeters is centimeters to the second power, or square centimeters. Again, if we leave this as a final answer, we're saying the sum is somewhere in the interval between 7.8535 and 7.8545 square centimeters. But in actuality, where could the sum really be? Well, at the smallest it would be is if we multiply the two smaller numbers, 3.35 times 2.305, which is 7.722175 square centimeters, and the highest it could be, or bound for the highest, would be to multiply the two upper bounds, 3.45 times 2.315, which is 7.98675 square centimeters. So that's what we, if we really want to be precise about this, we would give that as our interval that the product had to be in. But notice this is quite a bit different interval than what we were indicating above. So the way we're going to do this one is, when we multiply, we're going to go with the least number of significant digits is determining how many significant digits in our answer. So our inputs have significant digits of 2 and 3. The least of those, the weak length, is the 2 digits. So we're going to round ours off to 2 digits. So 7.845 square centimeters rounds off to 7.9 square centimeters, that should say. Need to fix that. I should say square centimeters. 7.9, AB equals 7.9 square centimeters. And so AB is in this interval, we claim, between 7.85 square centimeters and 8.05 square centimeters, which is much closer to, but still not exactly the same as what we really know. Again, if this is not precise enough for you, then you should have measured your stuff more precisely to begin with. Okay, so if you can measure there's no way we're going to take measurements that are rounded off to the nearest foot and get answers that are accurate to the nearest inch. So here are some basic rules that we're going to use as sort of a simplified rule. Again, it may still not line up exactly with the real possibilities, but it'll be close, and it's simpler, so we're going to use them. So when you're performing only addition or subtraction with measurements, round off all final answers to the precision of the least precise input. So in other words, the weak link in the chain is the measurement with the least precision. So this goes back to our example that we started with. I say I'm 9 miles from my office, and then I move an additional 6 inches. Do I say I'm 9 miles and 6 inches? Well, yeah, but then we need to round off to the appropriate number of appropriate level, which is still saying, well, I'm still 9 miles. That 6 inches is insignificant compared to the half a mile that we could be off just because of our measurement of 9 miles. So we're still going to round off to the nearest mile, which is our least precise measurement. Again, notice we often use equal to in measurements when we really should probably use approximately equal to. So here I'm going to say 9 miles plus 6 inches equals 9 miles. As pure numbers, that's not exactly right. 9 miles and 6 inches is 9 miles and 6 inches. It's not the same as, it's a little bit more, it's 6 inches more than 9 miles as a pure number. But as a measurement, these are approximately the same, and oftentimes properly speaking, we probably should use an approximately equal sign anytime we use a measurement. But we'll probably use equals a lot instead. So here's another example. If we take 4.5 centimeters plus 0.345 centimeters, go ahead and work it out. Give all the digits. 4.845 centimeters. But then, as a separate step at the end, determine where we need to round off. The first measurement was only measured to the nearest tenth, so that's the best we can do on our final answer. So that works out to be 4.8 centimeters. Now this is another very, very important thing here, so be sure that you get this. When performing computations with measurements, keep all the digits of the process. Every digit you can work out, or if you're using a calculator, every digit your calculator has. For the entire calculation, every step along the way, keep every single digit, never round off. And write that answer down with all the digits you have, and then as a separate final step, decide where you need to round off your final answer to the appropriate number of significant digits or the appropriate precision, and round that off. Never round off in the middle of a calculation. This can very easily get you an incorrect answer. So here's an example of where that show an illustration of that. So the correct way, if you have measurements of 9.84 times 3.554, would be multiply it all out, get the whole thing, 34.97136, and in this case we would go with 3 significant digits for our answer, and so that would be 35.0. That's the correct way. The incorrect way would be, say, well, we're going to need 3 significant digits, round everything off to 3 significant digits before we calculate, so that would be 9.84 times 3.55, that would be 34.932, then round that off again, that's 34.9. Notice that we're off a little bit. Depending on the numbers, it could be quite a bit, but at least that last digit could very well be suspect, and sometimes more than one digit could be off. So notice 35.0 and 34.9 are off a bit. That's a very easy way to miss a question. So never round off in the middle of a calculation. Now I've actually already used this once. We want to find the significant digits in a multiplication calculation. Now if the calculation is only addition and subtraction, remember, what previous slide said, that is, we go by the one that has the least precise answer, and that's the precision we go to, least precise input, and then our answer goes with that same precision. In multiplication calculations, or divisions and powers and roots, we're going to figure out how many significant digits are in each of the input measurements. We find out which one of these has the least number of significant digits, and that is the weak link in our chain. So you're going to round your final answer to this smallest number of significant digits. Again, this is a simplified rule. It may still overstate the known precision, or the interval may not line up exactly with the real interval as we've seen already. But this is a rule we're going to use for this class. It's a pretty standard rule. So for example, if we take 2.35 centimeters times 0.12 centimeters, we get 0.282 centimeters. All the digits again, no rounding off. Now we round off for our final answer. The inputs had 3 significant digits and then 2 significant digits. The weak link is the 0.12 centimeters, which only had 2 significant digits. So our answer is rounded to 2 significant digits, so that is 0.28. That 0 is not significant. Alright, so here's some practice using exactly what we just said. Use these simplified rules for deciding where to round it off. So you're going to work these out, not round it off, write that out first, then a final step would be rounding these off to the appropriate number of significant digits, the appropriate precision. Okay, go ahead and do this now. Press pause and then come back when you're done. Okay, so 3.35 meters plus 0.2451 is 3.5951 meters. And then, since this is all addition, we just go with the one that's least precise. The first one's got hundredths. The next one is smaller than that, 10 thousandths. So hundredths is the least precise, 2 decimal places, so we round off to 2 decimal places. The 5 in the third place is bigger than the 9, so we add 1 to the 9, makes it 10. So that leaves a 0 there. Regroup, pull it over to the next level, add it to the 5, that's 3.60 meters. Similarly, 4.5 centimeters minus 0.24 centimeters is 4.26 centimeters. The original data, the weakest one, least precise, was the first one, which was in tenths, and so we round this off to tenths, which is 4.3 centimeters. Next one's multiplication, so we just multiply 4.3 times 6.23, that's 26.789. Meters times meters is square meters, or meters to the second power. Look at the significant digits for multiplication and division. 2 significant digits and 3 significant digits. The least of that is 2, so our answer should have 2 significant digits. That would be the 2 and the 6. Look at the next one over as a 7, so add 1 makes 27 square meters. Similarly, 3.56 centimeters divided by 8.221 centimeters. You're probably going to want to pull out a calculator for this one. And that's approximately 0.43303734434. No units because the centimeters cancel out. And that's already been rounded off. It's actually a repeating decimal. Okay. But we're going to round it off some more because the original data had 3 significant digits and 4 significant digits. So this should be a 3 significant digit answer. The 0 is not significant. Point. Then the 433, 0 after that, so it's just 0.433. Now we're going to talk a little bit about something called scientific notation. Sometimes we need to express numbers whose absolute values are either very, very large, so they're very, very far away from 0 on the number line, or they're very, very small, they're very, very close to 0. And we want to avoid writing this with a whole bunch of insignificant zeros used only as placeholders. And so we have a notation for that called scientific notation. It's called scientific notation because scientists are the main people who have to deal with numbers that are this small or this large. And so basically what you do in scientific notation is all the digits that are significant, you list them down, and then you put sort of without reference to place value, and then right after the first one that's non-zero, there's going to be a decimal point and then the other digits. And then you multiply that number by 10 to some integer power so that the digits will have the proper place value. Now just remember what happens when you multiply by 10, everything jumps up one level in the place value, or dividing by 10 it goes down one level. So multiplying by 10 to the n raises the place value of each digit n times, so the decimal point is moved n digits to the right. Similarly, if n is a negative number, a negative integer, the decimal point's moved n digits to the left. So see if you can, so here's some examples of what these first 4 are actually in scientific notation, and you can see what they look like. We have a non-zero number, point, some other digits. All the digits you see in this first part are significant. So let's look at this. This is 3 significant digits, 3 significant digits, 4 significant digits, and 3 significant digits in these 4 exercise problems. Okay? So the number of digits you actually see they're all significant in scientific notation. And then it's times 10 to some power. Okay? And so we want to be able to convert this from scientific notation to standard notation, and then from standard to scientific. So you should be able to do this now, I think. Go ahead and do this now. Press pause and then come back when you're done. Press pause now. So when you say times 10 to the 5th, you're moving the decimal 5 places to the right. So it starts here between the 2 and the 3. Between the 3 and the 5 is 1, 2, and then 3, 4, 5 is going to require us to have 3 more zeros. So this is just a Another way of writing 235,000. Now, perhaps not so helpful for that one, but some of these others, when you get more and more decimal places you've been moving around, the better the scientific notation is. 1.05 times 10 to the negative 8, you move the decimal 8 places to the left. Once crosses the 1, and then you go, so what's here? 1, 2, 3, 4, 5, 6, 7, 8, and ends up there. So you have to fill in with 7 zeros. First zero on the additional 8th zero on the front is optional. Okay, 2.030 times 10 to the negative 15. That's a 0.14 zeros and the 2030. 6.02 times 10 to the 23rd. Well, 2 places going to the right. You need to move it 23 places to the right. 2 of those are counted for by the 0 and the 2, so you're going to have 21 zeros for placeholders, which is what we have here. So these are really, really huge numbers, particularly this last one, or really, really small numbers for the second and third example. Going the other direction, you see the only things that are significant are the 2, 5, and 0 in that order. So you put 2, 5, 0, put the decimal after the 2. How many places do we move the decimal to get the decimal there? Well, if we started with the decimal here at 2.50, we're going to go 1, 2, 3, 4, 5, 6, 7 places to the left, so that's times 10 to the negative 7th. Here, this next one, all these zeros in the beginning are insignificant. This 1, 0, 1, those are significant, so we put 1.01 and count how many places we moved it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 10 to the negative 12. Big numbers will have positive exponents on the 10. Small numbers will have negative exponents on the 10. 1,200,000. These zeros are considered non-significant, so all we have is the 1 and the 2, so that's 1.2. And if we look, that's 6 decimal places we move to the right, so it's 1.2 times 10 to the 6. The next one, the 1, 2, 3, and 5 are significant, so it's 1.235, and it's a total of 3, 6, 9, 12, 10 to the 12th, because we move the decimal. If we started at the 1.2, we would move it 12 places to the right to get the standard notation. Now we have units of measurement for real-world measurements. So some basic things that we might measure are length, area, and volume. So length is one of our most basic things, and what we're talking about is taking a unit line segment stacked in, set end to end, and counting how many of those will go along some straight path or curved path. So things that you can measure with a ruler or yardstick or a tape measure, even if a tape measure might have to bend along the path. Or you could wrap a string around it and then straighten the string out and measure with a ruler. Area is you take your line segment, then move it in a perpendicular way, you get a little unit square tile, and you want to see how many area of those little square tiles can lay across the surface. Volume, move that tile into the third dimension and we've got a little cube, and we want to see how many cubes will fit into a region of space. Or one nice property of a liquid is that it will take the shape of its container without changing the volume. So you could take a little unit cube container, fill it with water, then dump it into your object if it was hollow, and see how many times you would do that to fill it up. So we have some basic units of measurement. Now, in the ancient times, people used what was handy, pardon the pun. They would use their hand or their foot or other body parts. A cubit, for example, is from the elbow to the tip of the finger. A yard is from the nose out to the tip of the finger. Inch is with one of your finger, your thumb, and so forth. And so the foot, of course, is the length of your foot. So these are based on body parts, but of course you can obviously see some argument going on in some ancient marketplace when a guy comes and says, okay, I want 5 feet of rope, and he's got these big feet, he's thinking he's going to get a lot of rope, and the market vendor brings out his daughter to measure the rope, and she's got little bitty feet, and now we have a problem because a foot's not standard. So this became standardized, and eventually these became defined in terms of the metric system. But these are a most ancient system of measurements, and they have all kinds of crazy conversion factors. The metric system is a much better system because it all uses a consistent conversion, just like our numbers do, of base 10 to convert among the different units in the metric system. There's also a nice relationship between the meter, the gram, and the liter. And we also have the meter is ultimately based on well, a real-world thing that can be measured and it doesn't change. So the meter is the basic unit of length, the square meter is the basic unit of area, and the cubic meter or the liter are basic measurements of volume. That's the metric system. We do have an R in the as a unit of measurement, and there are a few others units of length as well in the metric system. In the American system, we have all kinds of lengths: inch, yard, foot, and mile are probably the most common, but there are also some others that you probably may have heard of but aren't used as commonly: hand, span, cubit, rod, furlong, mile, and so forth. The square of any length unit is a basic area unit, so square inches, square feet, square miles. But we also have some for land area, like an acre or a section in American units. And the cubic units of any length unit, like cubic inches, cubic feet, cubic miles, are volume units, but we also have all kinds of volume units. For example, if you're in the kitchen, teaspoon, tablespoon, fluid ounce, cup, pint, quart, gallon, and others like a grain, a bushel, a peck, a drop. There's several different ones there. Now within the metric system, they're related by prefixes. Okay, which I don't have a slide on that here. The main ones you need to remember is that 100 centimeters, centa is a hundredth, so 100 centa whatevers are 1 whatever. So 100 centimeters is 1 meter. 100 centiliters is 1 liter. Milli is the real common one. It means a thousandth. So 1,000 milligrams is 1 gram. 1,000 millimeters is 1 meter. 1,000 milliliters is 1 liter. And then the main other one that we're going to use is the kilo, which is 1,000. So 1 kilogram, okay, is 1,000 grams. 1,000 kilometer or kilometer is, or 1 kilometer is 1,000 meters, and so forth. Now on this page you're going to see several different conversion factors. Now almost the ones that are underlined are measurements, and so those have a certain amount of significant digits that have been rounded off. The others, though, however, are actually definitions, and we do have a font problem here. Angle measurements, that should say pi radians equals 80 degrees. 60 minutes equals 1 degree. 60 seconds equals 1 minute. That's the way you read those at the bottom in the center. 1 inch is now by definition 2.54 centimeters exactly. It didn't start out that way, but that's going to be our current definition for it. So anytime you use these figures in a computation, for example, they're infinitely precise. So for example, if I use the fact that 1 foot equals 12 inches, that's not a 2 significant digits thing or 1 significant digit. That's infinitely many significant digits. because 12 inches is exactly 1 foot. That's a definition of what 1 foot is. So most of these in here you should kind of know. Some of these things you may not know the full out, but maybe 454 grams for 1 pound, something like that might make sense to know. So how do we convert between two units of measurement? So for example, let's take a calendar year that's exactly 1 year on a calendar and see how many seconds that would be. Well, 1 year is 1 year over 1, and what we do is we multiply by a fraction that's equal to 1. So notice 365 days is 1 year, at least for the most standard calendar years. And notice if I multiply these together, since the 365 days equals 1 year, that second fraction there, 365 days over 1 year, is equal to 1. When you multiply by 1, that's the identity property. It stays the same. So we're not changing the actual amount, we're just changing the units. And so notice the years will cancel and we'll be in days. Next, we multiply by 24 hours over 1 day. Notice we had days in the top, we need days in the bottom to cancel out. Then 60 minutes over 1 hour and 60 seconds over 1 minute. And if you look, everything cancels as you're going across. The years cancel, then days, then hours, then minutes. And the only thing that doesn't cancel is seconds, which is in the numerator. And so we're going to have seconds in the numerator where we want it to be for our final answer. Okay, then you just take the numbers and work this out. You can do this with a calculator real easily. Start with 1, then say times 365, times 24, times 60, times 60. If it's in the top, just multiply. If it's a number in the bottom, divide by it. You can kind of ignore the ones because multiplying or dividing by 1 doesn't change the number. So you could just type in your calculator 365 times 24 times 60 times 60, and this is 31,536,000 seconds. And that's to the nearest second if we think of this as an exact amount. Okay? Alright, if this was a measurement, we said approximately 1 year, then that's only one significant digit, we'd just say 30,000 seconds. 30 million seconds, excuse me. Alright, here's some more examples. So suppose we want to take 3,714.3 meters to kilometers. 1 kilometer is 1,000 meters. If we put the 1 kilometer on the top, 1,000 meters on the bottom, we see the meters cancel. We're dividing by 1,000, which moves the decimal 3 places to the left. So that's 3.7143 kilometers. 30.077 kilometers we want to convert to millimeters. 1,000 meters is 1 kilometer, and 1,000 millimeters is 1 meter. I've arranged these in such a way that both the meters and kilometers cancel, and so we're multiplying by 1,000 moves the decimal 3 to the right, and then another 1,000 moves it 3 more to the right. So that's 30077 and 3 more zeros, 30,077,000 millimeters. We want to convert from decimal degrees to radians. Radians is technically not a unit. So we have 78.126 degrees. We multiply by pi, radians, over 180 degrees. The degrees cancel, and that approximately works out to be 1.363555931. Notice here I've worked it all the way out, all the digits, but then I round off. There are 5 significant digits in the original problem. The pi and the 180 are exact. Of course, the pi is limited by how many digits I have in my calculator, but it's a lot more than the 78.126 has. So the weak link is a 78.126, which is 5 significant digits. And so that is 1.3636 rounded off. Notice I did not use, in this I did use the pi button on my calculator. I did not use some decimal approximation like 3 for pi. If I used 3 for pi, I wouldn't get this number here, but my answer would be limited by the approximation I used for pi. We'd only have a 1-digit answer. Or if I used 3.14, I would only have 3-digit answer. We don't want that to be our weak link. We want our weak link to be the actual measurement that was taken or given to us. So I want to be sure that I use all the digits my calculator has for pi. In other words, just use the pi button. Similarly, if we want to take 1.459 radians and turn it to degrees, this time I multiply by 180 degrees over pi. There's nothing really to cancel out in units here, but I want my degrees at the top and the end. And this one is actually rounded off incorrectly. There should be 4 significant digits in the answer, so it should be 83.59 degrees. 83.59 degrees. I'll fix that for the handout. 216.7 feet. We want to put it into feet and inches. Well, that's 216 feet plus 0.7 feet, so we know we have 216 feet. We need to convert the 0.7 feet into inches by multiplying by 12 inches over 1 foot, and that turns out to be 8.4 inches. Probably should actually round off that one to the nearest inch in this case, 8 inches. So you probably should say 216 feet, 8 inches. Suppose we have yards, feet, and inches. 12 yards, 2 feet, 9 inches. When we want to convert that to, say, feet. Well, 12 yards is 3 feet per 1 yard. So that's 36 feet, plus the 2 feet is 38 feet. And the 9 inches, we multiply by 1 foot over 12 inches to get 0.75 feet. So that's 38.75 feet. If this was exact, that would be the exact answer. If the 9 inches is rounded off to the nearest inch, I probably need to go ahead and round this off to 38.8 feet. Degrees, minutes, and second to decimal degrees. 46 degrees, 51 minutes, 11 seconds means 46 degrees plus 51 minutes plus 11 seconds. A minute in angles is 1/60th of a degree, so 60 minutes equals 1 degree. So if I multiply the 51 minutes by 1 degree over 60 minutes, the minutes cancel and I get degrees. I take the 11 seconds, multiply by 1 minute over 60 seconds, the seconds cancel, and I multiply by 1 degree over 60 minutes, the minutes cancel, so I also get degrees. Degrees plus degrees plus degrees gives me degrees. I can do this on my calculator all together and say 46 plus 51 divided by 60 plus 11 divided by 60 divided by 60, enter, and I get 46.85305 with the 5 repeating degrees. And if I round off, it turns out to the nearest second is about the same as the 3 decimal places on the degrees. That's a close approximation. So, what kinds of things did we talk about in this lecture, and what should you be able to do? Well, you should be able to explain the difference in pure numbers and measurements, determine the number of significant digits and the precision indicated by a stated measurement, find the maximum error and maximum relative error. We actually haven't done that one due to rounding off. The maximum relative error, let me tell you about that, is you take the maximum error and then divide by the original measurement, making that a percentage. Okay? So sometimes it's not so much how big is the error, but how big a percentage of the original measurement is an error. For example, being off by an inch is maybe not too far measuring across the room. It's maybe quite a bit if we're trying to measure how wide a book is. If we're measuring the distance from Fort Smith to New York City, 1 inch is totally insignificant. It's still 1 inch, no matter how we do it, but as a percentage of the measurement, it's very different in those examples. So a relative error means percentage error. So you just divide the maximum error by the original measurement. You should be able to round off numbers to a specified decimal place or indicated number of significant digits. You should be able to convert between standard and scientific notations. You should be able to perform computations using scientific notation or standard notation. You should be able to state, recognize, and use some standard units of measure in the metric system and the American system. And by the way, I do call it the American system. I've heard other people call it the English system or whatever. It may have come from there originally, but no one in the entire world, in terms of industrialized countries, use such a crazy system as the United States. Everybody uses the metric system except for us. So really it is the American system. We're the only people that use it. You should be able to state from memory basic conversion factors among the basic units of measure and convert measurements from one unit to another with or without a calculator, but especially with a calculator. And demonstrate a mastery of knowledge of when to avoid rounding off, like in the middle of a calculation, and when to round off at the end of the calculation, and to what place by some of their little rules that we've determined. Okay, so there we've gone over some measurements and approximations.